My lab is the coolest place in the universe. And I do mean that quite literally, because in my experiment, we take a few million atoms and cool them down until they're 10 million times colder than the depths of outer space. We do this because when atoms get this cold, they form a single giant quantum state, which just means that we've got all of these millions of atoms acting effectively as though they're just one atom. But because there are so many of them, it becomes quite easy for us to just change the environment that they're in or the interactions between them. And if we want to see the results of this, our system's so big that all we have to do is put in a camera and take a picture. So this means that we can use cold atoms to investigate systems that are just too difficult to directly access experimentally or sometimes even to calculate. And a really interesting example of this is electrons in a magnetic field on two-dimensional semiconductor surfaces. So experiments have shown that these electrons should have fractional charges, which is strange because electrons are meant to be elementary particles, so their properties are absolutely fundamental. And this raises the question of how fundamental these charges can really be if they can in fact be fractured. As well as these kind of fundamental physics questions, we're interested in these states because they could be useful in quantum computing, which would completely revolutionize the computing power that we have access to. But the difficulty is that to study them, we need incredibly strong magnetic fields. And furthermore, the electrons that we're interested in are stuck on the surface of a block of semiconductor. So how are we meant to get control of the interactions and really find out what's going on? Well, fortunately, as you can see on my slide up there, electrons in a magnetic field are mathematically equivalent to rotating neutral atoms. So if only we could somehow control some atoms, we could dress them up like electrons and use them to solve the problem. Which brings me right back to my cold atom experiment. So we trap our atoms, that giant quantum state, on a two-dimensional surface, which we deform to make the atoms rotate. And if they rotate fast enough, we expect to see the exact same fractured states emerging. But the difference now will be that we have control over the system at the individual atom level. So we can truly study and ultimately understand and learn to exploit the strange behavior of electron fracture. Now this is a work in progress. We can trap our atoms, rotate them, just not fast enough yet. But our results, when we get them, will be a stunning demonstration of the power of cold atoms to solve truly fascinating, but seemingly intractable problems.